Welcome back, Design Junkies, to Mechanical Engineering Made Simple. So today we're going to try something a little different. We're taking lean principles, the stuff usually associated with the factory floor, and dragging them kicking and screaming into the engineering office. We're diving into lean engineering. Basically, how do you apply that relentless focus on cutting waste and boosting value across the entire product development process?
Exactly. It's about seeing the whole operation from that first glimmer of an idea all the way to shipping the product as well, a single complex system.
Right, not just optimizing isolated parts.
Because historically, yes, lean was about streamlining the assembly line, but we've come to realize that the biggest cost commitments, the really impactful ones, they happen way before anyone picks up a wrench. So our core mission here is really about accelerating the whole cycle time. Getting rid of waste, yes, but also setting up really efficient standard processes. And this is where you start hearing about things like integrated product and process development, IPCD.
IPPD. Sounds a bit like jargon, maybe? Let's make it real. We're talking about pulling everything together. Design specs, manufacturing needs, supply chain, logistics right from the get-go, aren't we?
Pretty much. Integration from day one. Okay, so let's start at the beginning. Product development, or PD, what is it?
Well, the way I see it, PD starts the moment you spot a gap in the market, some opportunity. And it doesn't really stop until that product is being made, sold, and crucially, delivered successfully. It's the whole 9 yards.
It is the whole marathon. And if PDO, a marathon, the main thing you're actually creating along the way is, well, it's uncertainty reduction.
Uncertainty reduction. Okay, unpack that a bit.
Think about it. Every activity in product development, every design choice, every simulation, every prototype test, it's fundamentally about gathering information to kill risk. Every dollar spent, every hour invested should be chipping away at what you don't know. So as time goes on, that risk level should be dropping sharply, while the value you're locking in should be climbing just as fast.
That makes sense. But it raises the question of where this uncertainty actually comes from. Risk is about the unknowns.
Right. And engineers, project managers, they're used to dealing with the known unknowns. The tests they know they need to run, the data points they know they're missing. That's part of the plan.
But the real curveballs.
Those are the unknown unknowns, the things you didn't even know you didn't know. Maybe an unexpected material interaction, a sudden shift in regulations, or a competitor coming out of left field. Lean PD tries to use really fast feedback and concurrent work to surface those nasty surprises as early as humanly possible.
And timing is it's everything here, isn't it? Because design's so interconnected, those early decisions have these huge ripple effects. I remember seeing this classic graph.
Oh, that three-curve graph. It's
Yeah.
practically scripture in systems engineering. It shows ease of change plummeting almost immediately, right there in the conceptual phase.
So making changes is cheap early on.
Dirt cheap. You can pivot the whole design for almost nothing. But, flip side, costs incurred the money you're actually spending, and more importantly, life cycle cost committed, the LCC. They spike upwards incredibly steeply right then during preliminary design. An engineer choosing, say, a slightly cheaper component today might unknowingly commit the company to hundreds of thousands in extra maintenance or unique spare parts over the next decade.
Wow. So waiting to resolve uncertainty doesn't just cost a bit more. It costs exponentially more later on.
Exactly. The penalty multiplies, which means you absolutely need tools and methods that force collaborative, informed decisions early, locking in the right LCC profile.
And that leads us naturally to things like integrated concurrent engineering, ICE, and its sort of evolution, real-time concurrent engineering, RTCE.
Right. ICE, which got its start at places like JPL, isn't just about having more meetings. It's fundamentally about doing the actual design work together, simultaneously.
Not just status updates.
No, not at all. You've got stress analysis, thermal, electrical manufacturing folks, all working in parallel. The magic ingredient is usually a central server, a single source of truth. All the design data flows through it. So if you're the thermal engineer, you see the structural engineer's latest bracket update the instant they commit it. No waiting for drawings, no outdated information.
I can imagine that's maybe a bit unnerving for engineers used to working in silos, but the benefits must be significant, that instant visibility.
It changes everything. First, it drastically cuts down information lag and the blame game that comes with it. Second, and this is crucial, it shifts decision-making. It moves away from subjective calls and, design by seniority, where the person with the fanciest title wins towards objective, data-driven choices.
How so?
Well, If the structural engineer uploads a design and the thermal simulation running automatically flags it as overheating within minutes, the data makes the decision. It's not about who argues best.
And the speed improvements reported are, well, they're pretty staggering. Some teams getting new designs done in hours instead of weeks.
Yes, the metrics are often dramatic. We've seen lead times for standard design tasks cut by a third or more. And that ability to generate a viable new concept design in, say, 4 hours versus 4 weeks, that's not just faster, it's strategically different. It means you could explore maybe 4 completely different architectures in a single day instead of spending a month just validating one. You cover the design space much more effectively.
Finding the global optimum, not just the first acceptable solution.
Precisely. And this drive for efficiency also brings up another key lean idea: variability reduction through design for reuse.
Okay, design for reuse, like
Yeah.
using standard parts or making things symmetrical.
Exactly that kind of thing. Multi-use parts. For example, designing a component so the same part works on both the left-hand and right-hand side of an assembly, maybe just by flipping it over, or making it a true mirror image.
Seems basic, maybe.
It seems basic, but the downstream effects are enormous. Fewer unique part numbers to manage, which means lower inventory costs, less tooling complexity, reduced chance of assembly errors. Think about the person on the assembly line. If the parts are symmetrical, they can't install it backwards. Fewer mistakes, less rework, lower cost. It cascades.
Right. And to do that effectively, you can't just think about your own design task. You need to consider manufacturing, assembly, even maintenance down the line. This forces a wider view.
It absolutely does. It forces you to zoom out and think about the entire system, the extended enterprise.
Okay, the extended enterprise. Let's define that.
A lean enterprise isn't just the company itself. It's this integrated entity that creates value for all its stakeholders, this whole network.
Stakeholders. That word gets used a lot. How are we defining it here in this systemic lean context?
Good question. Here, a stakeholder is basically any group or individual who can affect or is affected by the enterprise's value creation processes, directly or indirectly.
That sounds incredibly broad. Customers, employees, suppliers, sure. But regulators, the media, local communities.
Yes, potentially all of them. Which leads to the next critical question. How do you figure out who actually matters most? You can't cater to everyone equally all the time.
So how do you prioritize? How do you map their relevance? Or what's the term?
Salience, stakeholder salience. It's generally seen as having 3 key attributes. First is power.
Power meaning...
Influence.
Exactly. The ability to make the enterprise do something it wouldn't otherwise do. This could be coercive power, like a regulator threatening fines, utilitarian power, like a major customer threatening to walk, or even symbolic power, like negative media coverage hurting your brand.
Okay, power. What's number 2?
Legitimacy. This is about perception. Is the stakeholder's claim or action seen as desirable, proper, or appropriate within the norms and values of the organization or society?
So does the stakeholder have a right to make this demand?
Sort of.
Yeah.
A union demanding safer working conditions usually has high legitimacy. A competitor spreading false rumors has very low legitimacy. Got it. Power, legitimacy. And the third attribute.
Criticality. This one often involves time sensitivity or the sheer importance of the claim to the stakeholder.
Okay, explain criticality a bit more.
Think of a small supplier who is about to go bankrupt if you don't pay their overdue invoice today. That's high criticality due to time sensitivity. Or think of a community group demanding you address toxic runoff that's vital to their local environment. The importance of the claim itself gives it criticality.
So power, legitimacy, criticality. You use these 3 factors to sort of triage the stakeholder network and figure out who needs attention when.
That's the idea. It helps make sense of that complex web. And there are conceptual models to help visualize this.
Like the one mentioned in the research, the water drop model.
Yes, the water drop model. It's a qualitative tool, not quantitative, but it helps picture the relationships. Imagine the company as the point where a stone hits the water. The first ripple, right next to the impact point, those are your primary stakeholders. Key suppliers, your core employees, your most loyal customers. They have direct, frequent interactions and high interdependence with the firm.
And the ripples spread outwards.
Exactly. Those primary stakeholders have their own stakeholders, their suppliers, their employees, their communities. These become your secondary stakeholders. Think government agencies, the media, activist groups. Their influence on your firm is often mediated through those primary stakeholders. A new regulation, secondary, impacts your supplier, primary, which then impacts you.
So it shows these nested recursive relationships. Your connection with the supplier isn't just about price, it's influenced by their relationship with their bank or their local government,
Precisely. It highlights the interconnectedness of the whole system.
which actually provides a really smooth transition. If the extended enterprise is this sensitive, interconnected system, then managing the physical flow of goods through it, the supply chain also needs a systemic approach to avoid creating chaos.
Absolutely. Which brings us squarely to Heijunka.
Heijunka, a Japanese term, right? From Toyota Production System.
That's right. It literally means leveling. It's the process of smoothing out production, both in terms of overall volume and the mix of different products being made. It's fundamental to TPS stability.
And it's designed to combat.
Yeah.
What's that classic supply chain problem, the bullwhip effect?
The dreaded bullwhip effect, yes. Heijunka is the antidote. The bullwhip often happens because of perfectly rational local optimization decisions that cause massive upstream volatility.
Give us an example of that local optimization causing trouble.
Okay, imagine a trucking planner for a regional distribution network. Their main performance metric might be truck fullness to minimize transportation costs per unit. Seems sensible, right?
Yeah, you want full trucks.
So to get full trucks, the planner waits until they have a large order for a specific product, say product A, going to a specific warehouse. They send a massive batch, maybe a whole week's or month's worth all at once. Then maybe nothing for days.
Okay, see where this is going.
That big batched order hits the central warehouse or factory like a shock wave. They see a huge spike in demand for product A, so they scramble, ramp up production, maybe pay overtime. Sure. Only for the next signal from that region to be zero for product A, but maybe now a huge spike for product B. The regional centers swing wildly between being swamped with inventory and being completely starved.
Yeah.
And that variability gets amplified further and further upstream.
It's classic sub-optimization, making one small part look efficient while crippling the whole system's performance.
Exactly. The lean approach, using Heijunka, says, forget optimizing individual truckloads locally. We need to establish a level, predictable flow for the system. So maybe the Heijunka control dictates sending, say, 4 smaller mix-load trucks every single day to that regional warehouse. The volume is level, the mix is level.
Even if the trucks aren't always 100% full.
Even then, because that stability, that predictability is incredibly valuable, it dramatically reduces the signal variability going upstream.
And that stability allows the manufacturing plants to
optimize globally. Precisely. When the factory sees a smooth, predictable demand signal, they can stop reacting to phantom spikes and troughs. They can implement much more sophisticated scheduling, maybe moving towards producing every part every day in smaller quantities, rather than doing massive, inefficient changeovers between huge batches.
So leveling the downstream flow enables efficiency upstream.
That's the core idea. And implementing this often requires more than just organizational changes. You need the analysis to back it up.
Right. These aren't just policy decisions. You need the numbers.
Absolutely. Technical modeling, simulation, they're critical. You might use simulation to compare different distribution strategies. You definitely use financial tools, like net present value analysis, to compare the total system costs of, say, the full truckload batching scenario versus the level flow Heijunka scenario, factoring in inventory costs, stockout costs, overtime, everything. These quantitative tools are essential for synthesizing all the different factors, logistics, finance, production, and helping everyone reach consensus on the best system-level design.
It really strikes me how this all ties together. Whether we're talking about RTCE managing design risk early on or Heijunka managing supply chain variability later, the underlying principle is this holistic systems view across the entire value stream.
That's the essence of it. Product development, manufacturing, distribution, they aren't separate fiefdoms. They're interconnected parts of one value-creating system.
So the goal of a truly lean enterprise is this deep integration.
Yes. And if you accept that the enterprise is a complex system, then its ability to adapt and evolve successfully seems to depend on something researchers call complexity partitioning.
Complexity partitioning. Okay, sounds intriguing. How would you explain that in maybe simpler terms for an engineer on the ground?
Think about biology, like the human genome. It's a masterclass in partitioning complexity. You have parts that are incredibly stable and conserve the core protein coding genes, the exons. They represent the reliable, proven functions. Variability there is usually bad.
Okay, the stable core.
But then you have other vast regions of DNA, historically called junk DNA, which exhibit much higher variability. These regions are now understood to be crucial for regulation, for enabling architectural recombination, for innovation, for trying out new structures without breaking the core functions.
So high stability in some areas, high variability allowed in others.
Exactly. A successful lean enterprise arguably needs to do the same thing. It needs to strategically decide where to enforce stability and low variability things, standardized core processes, validated multi-use components that level Heijunka schedule, protect the essential value stream. But it also needs areas where flexibility, experimentation, and innovation can thrive, maybe in exploring new product features, trying radical process improvements in contained pilots, or allowing more architectural freedom in non-critical modules.
So you partition the system, protect the stable core, innovate at the edges.
That seems to be the pattern. You need both stability for efficiency and reliability and controlled variability for adaptation and future growth. Finding that balance, that's the ongoing strategic challenge.
Protecting the core value stream while enabling dynamic change elsewhere. A fascinating thought to end on. Until the next equation, Design Junkies. Tune in every morning at 11.